Hello, this is Stuart Mason for Math E156, Math 156, and we're doing 10C, a normal Bayesian example. I must say I'm delighted with this course's treatment of this material so far. When I took a stat course that taught me this, I had to do all the messy algebra and start from the prior and turn it into the posterior. I love that we're just taking the results and using them, because that really is the important part. Although, of course, understanding where they come from and how is key to knowing how to use them effectively. But cool. So previously we saw a beta binomial example. So we have some beta prior, we update it with a binomial trials, and the result is a beta posterior. Now we're going to start with a normal prior and update it with some data vector that we assume is also distributed normal, and the result is finally a normally distributed posterior that incorporates information from both the prior and the data. So there's a little story about some ichthyologist sampling fish, and the textbook assumption of the fish length is one thing, specifically this, so standard deviation of 6 and a mean of 50, and she goes out and catches and tags 15 fish and measures them and updates her belief. So the formula from the textbook are messy to derive but not messy to work with. Basically the new variance is they kind of like, if any of you are familiar with circuitry, they kind of add in parallel. So it's the inverse of the sum of their inverses, and we call the inverse the precision. So basically you sum the precision and turn that into a variance, and you weight the data by how much data you have. And this is kind of cool. You know, if you think about, like, when you call it precision and you're just adding precision, that really intuitively shows you what's going on. So 15 is our data, 8 squared is the variance, assumed to be 8. So the thing is, if you allow the variance to be unknown, similar to like the t distribution arising out of that problem, this math gets messier. So we're just going to stick with the case where the variance is known. In the case where you need to learn the variance, it's basically a gamma problem, which the textbook offers some places to go if you're curious. But we'll just power ahead with the calculations, and this is now the standard deviation of the posterior mean, so the variance is going to be just under 4. And now the posterior mean is just the weighted average. Look at that. Now we've computed the new mean, the new standard deviation. So in red we can draw the posterior normal distribution. And now just to see the actual data, so in some old versions of this script there was an M1 here, which is incorrect. We're trying to draw like how the data were distributed there. So this is what we thought the distribution was. This is how our data were distributed, and there's 15 samples from this distribution, and so the result gives us this posterior, which, as the book points out, is swamped by the data, meaning like most of the information here comes from the data, but you can see it is pulled a little bit to the right by the presence of the prior, and it's also tighter. So the variance is reduced from well down from the prior, but also down from the data. So we have achieved a better estimate than either of the two alone. Topic 2 is kind of a sanity check. So one of the things that Bayesians are quite proud of is the way that you can update sequentially your information and get self-consistent results, unlike in a frequentist test where if you run the test 20 times with a true null hypothesis, one of those times you're probably going to reject it. Now, there's still the probability of type 1 errors in Bayesian statistics, but multiple testing does not present an increased probability of a type 1 error the same way it does for frequentists. Okay, so all he's done is break this example into instead of getting 15 fish, we're getting fish 5 at a time. So we're going to get 3 posteriors as we go, and use the previous posterior as the prior for the next step. So Here's the first 5 fish. So this is prior, posterior after 5 fish, which now becomes our prior. So this is the new assumption about the world. And now we're going to add in 5 more fish, and we get a new posterior distribution. So this blue posterior after 10 fish becomes our prior for the final 5, and the result is going to be the exact same posterior we got in the first place when we did all 15 data points at once. And as we add more data, the mean will get closer to the truth, and the variance will get tighter and tighter, but that's nothing new. Cool, so nice, quick, and easy example. The main point is that if you have a normal prior, you get a normal posterior, and the formula for updating the mean and variance you can just use freely without worrying about the derivation. So hope this was helpful, and I'll see you guys on Wednesday.